Hi, I'm Michelle Blackwood. I'm with Friends of Shades Creek. We're here on Ruffner Mountain today. This is two of the trails on Ruffner Mountain, and we're here pretty much on the ridge of Ruffner Mountain. So on my left, if it rained, the water would be going to the Warrior River. It would go first to Village Creek and then into the Warrior River. On my right, water that rains on this side will go into Shades Creek and then ultimately into the Cahaba and then to the Alabama River and down to Mobile Bay and the Gulf of Mexico. The water actually ends up in the same place, both directions. It starts in the same place, but it takes two very different routes. So we're here today to talk about the forest here on Ruffner Mountain. There's a beautiful forest here, and the trees and the forests are very important to a watershed, not only in the valleys where along the streams, but also at the top of the ridges, because it helps slow down the water. You'll see that there's plenty of leaves and roots and sticks to help the water slow down and soak into the environment. It keeps it from flooding once it gets downstream, and that's a good thing. It's not only a good thing for the trees and the forest, but it's also a good thing for the people that live down the mountain in homes that don't want to be flooded. So we're going to be talking about some interesting and some unique tree species, and I have my friends along with me to do that talking. We have Carl and Henry, and they'll be telling you more about the trees and why these trees live here.
I'm Carl. I'm one of the part-time naturalists here at Ruffner, so I've been here for several years helping them with whatever they ask me to do. I also work with the Alabama Paleontological Society, which makes it an interesting combination here at Ruffner because the geology is what really brought this whole project together here. So what we're doing, we're on one of the trails that leads down to the old limestone quarry. There were 3 limestone quarries here, and this trail heads down to the biggest one. It's about 1.25 miles from the entrance to the park. And these quarries then, they were not only mining iron ore, both strip mining and underground mines, they also had to have limestone to mix with the iron in the furnace at Sloan in order to get the iron out of the iron rock layer that it was in. And so these quarries are now still here, and as you hike along the trail, if you go down the quarry trail from the park entrance, as you come to the trail that leads into the largest limestone quarry, you reach a point where you can actually tell where you're walking out of the iron containing rock and into the limestone containing rock. And so what you can see, if you know what to look for, you can tell the difference. The iron has a reddish brown color, the limestone is a much lighter gray. And on a day when the sun is in the right position, when you walk this trail, you can actually see where you're walking out of the iron layer and into the limestone layer. And both of these ingredients were necessary to get the iron ore out of the rock and into the furnace and into the molds that they used that for. So the iron is Silurian iron. The limestone is Ordovician. They call it the Cambrian overlook up here, but it's not Cambrian rock. It's Ordovician. And those date roughly, the iron 400 million plus, the limestone is older. And so these were both formed in shallow seas that were here. So it took a long time. When we go into the quarry, you'll see how thick the rock layer is. It took a long time for the organisms that make up limestone to form these thick layers of limestone that are here now. And the iron too, the thick layers of iron that we have. Took quite a bit of time to form. But that's what brought people to the Birmingham area, was to use this resource and make an industry from it. So when these iron deposits were forming, the iron was in solution in water. When algae began photosynthesizing and producing oxygen, oxygen and iron naturally attract very rapidly. They really like each other. And when enough of that begins to combine, it begins to form a solid. It flocculates. And that material then piles up. And that's what formed these dense layers of iron over many, many, many years to make these deposits that have been mined here. And of course, iron is critical to us and most air-breathing animals because that's what carries the oxygen we inhale to the rest of our bodies. And so, the iron that we have is what I've been told is particularly good for making the type of products that were created from the iron that came from Sloan's furnace. It was not as good for making the type of steel that's in iron today. So that's why it's no longer mined here. There's still plenty of iron here. It's just there's no longer being mined. It's not, the economics aren't right for it anymore. The limestone, of course, formed in a shallow sea, and when it formed, it's not in the position where it is now. It was thousands of miles further south. Everything's been moving since then. And of course, limestone is the formation from sea creatures that have shells. When those creatures die and their shells collect on the seafloor, it forms a sediment layer that over time then becomes limestone. So when limestone is a sedimentary rock, dissolves in water sometimes. Under heat and pressure, this limestone metamorphic becomes marble. And that was what was mined at Sylacauga, the rich marble deposits there, that very high quality marble. But that didn't happen here at Ruffner. So both of these are used to mix in the furnace, and when it gets hot enough, the sandstone that makes up the iron matrix combines with the limestone, and in the furnace that material floats to the surface. The iron sinks to the bottom and is drawn off into whatever mold they're going to put it into. And then that slag material, when it cools, has been used to make bedding for railroad tracks and fill material for roads and other things like that.
We're in what we call the eastern deciduous forest. It extends down from Canada, New England, all the way down to the southeastern United States and on over to East Texas. The main genera of this forest are the oaks, the hickories, and the pines. So you would call where we are here at Ruffner Mountain the oak, hickory, pine forest. There are probably a dozen or so oak species here and maybe 4 or 5 hickory species. And a little further defined the characteristic of this forest is that we are in an upland site. So there are going to be trees that are native to the higher, drier ridges of Ruffner Mountain that we're going to find here. Carl just mentioned that we're at the divide between an iron-based soil and a limestone-based soil. And one indicator of that is a particular species called the Chinkapin Oak, Quercus muhlenbergii. And we are right at the dividing line where when you walk down the trail to the quarry entrance, you'll suddenly see Chinkapin Oaks, right where the geology changes. So I want to emphasize this tree. The leaves of the Chinkapin Oak are these. We kept a green one from last fall, and now that the leaves have fallen, they've turned brown and they are accumulating on the ground. And they're very important for soil development. The leaves will fall down onto the soil and decay and form the organic layer of the topsoil. So it's very important for tree growth to have these leaves cycling their nutrients and the organic matter into the topsoil, which is the same as the root zone. So the trees are growing in the topsoil or the root zone that's maybe 6 to 18 inches deep in the Birmingham area. A tree that is related, and you might confuse it with Chinkapin oak, is the chestnut oak, another upland oak species. But notice that the lobes of the leaves are more rounded, more scalloped. than the sharp pointy leaves of the chinkapin. So just to compare the two, they're easy to identify when you see them side by side. We'll also look at the differences in the bark and show you how you can distinguish them that way. So as we walk through the limestone area, we'll see more and more Chinkapin oaks. They become very prevalent here at the base of the quarry at Ruffner Mountain. And then we'll look at another species inside the quarry, the eastern red cedar, which also indicates limestone. So we'll head on down the trail from here. We're looking at two Chinkapin oaks. You'll often find them growing in groups. So we have two here right off the trail, easily visible. And the bark of these is a lighter gray color and fairly scaly bark. So you see, much like the bark of the pines we've looked at before, the bark is very fine and scaly on the Chinkapin oak, in contrast to the more deeply fissured bark of the chestnut oak, which we'll look at. Right across the trail from the two Chinkapin oaks we just saw is a larger Chinkapin oak. It is probably at least 70 years old, possibly well over 100. Hard to say whether mining was done right here or not, whether this is a natural layer of limestone or whether it was disturbed during the mining process. But if it was not disturbed, it could be well over 100 years old. These oak trees and these hickory trees are what I call our iconic megaflora of the Birmingham area. These are the oldest trees, the trees that have been with us the longest and represent the oldest trees in the area. These are our giant sequoias, our redwoods, our Joshua trees of the Birmingham area. So they really harken back to an earlier time. And they're still with us, and they're regenerating. So this is a naturally regenerating forest. It's doing very well, and that's one thing we like to see in a forest, to see the smaller trees coming on from as progeny of the larger trees. So a perfect example of the limestone-based soil, the Chinkapin oak growing directly out of that soil that has been derived from the limestone bedrock. These trees are not just standalone icons in our landscape. They support other species of plants and animals, even on their bark and in their limbs. If you look at this Chinkapin oak, you'll see a healthy stand of resurrection fern that is now dried out because we haven't had rain in a few days. But when we do have rain, the resurrection fern suddenly flushes out and becomes green. So just a good example of how these older trees support habitats for other microflora and all kinds of insects that birds feed on. So the oaks are very important for our bird populations, migratory birds. Hundreds of species of insects reproduce on these oaks. And on the flyway for migratory birds, they're very important food sources for many songbirds. We're just a few feet down the trail from where we saw the Chinkapin oaks before, and right at the entrance to the quarry. And you'll notice, looking around here if you come, that there are many more Chinkapin oaks around here. In fact, it's the most prevalent oak species surrounding the entrance to the quarry. Another limestone-based species is the eastern red cedar, which we're beginning to see here on the other side of the trail here on the limestone rocks. And it is actually a juniper. The scientific name is Juniperus virginiana, but we call it a cedar, eastern red cedar, for convenience. It's a tree with very durable wood that you'll find growing on limestone-based soils all throughout the Black Belt of Alabama. It's called dioecious, meaning two houses in Greek. They have separate male and female trees. So the female trees have the iconic blue berry-like cones. They're actually cones, so they're identified as conifers. So these are very important for wildlife. A lot of songbirds will eat the eastern red cedar berries or cones. And you'll see it become more and more prevalent the more limestone area, extensive the limestone area is. So we'll walk inside the quarry and look at some cedars inside. The leaves, in contrast to the pines, are not needle-like, but we call these scale-like. So the leaves are very, very small, growing in tandem on these little stalks, the little scales, and those are actually the leaves of the juniper, the eastern red cedar. So we'll walk inside and take a look more at the landscape position of the eastern red cedar inside the quarry.
Okay, we're in the largest of the limestone quarries here on Ruffner Mountain, and what we have here is the limestone layer would be quarried. There was a rail line that was just off to the side over here where the rock would be taken directly to the rail line and then on over to Sloan. And the quarry, since they quit mining here, has begun to go through ecological succession and is gradually growing back to a natural forest, although they haven't mined here since the 1950s, so you can see it takes a fair amount of time for nature to repair or come back to what it normally would want to have here. The limestone, like I said before, is Ordovician, and because of its age, the way it was formed, there is some fossil evidence still present, although it's rare. So it was on its way to becoming marble, but that got interrupted.
The top of the limestone shows the development of soil. Soil is both mineral and organic in nature, so the weathering of the limestone produces smaller particles that roots can grow in. Freezing and thawing, the action of rain, the action of roots themselves growing, and the organic acids given off by roots all break down the surface of the limestone here, and then new organic matter accumulates on top of that and turns into a layer of soil. So you have both organic and mineral components of the soil. On top of this limestone soil, we see the eastern red cedar taking hold and beginning a process of succession where certain species come in first, and then when they become established, the second round of species comes in and grows with them for a while and often takes their place. So we call that forest succession. So in this early forest succession here, we see the eastern red cedar dominant in the landscape because of its preference for a limestone-based soil.
All right, so this limestone forms, of course, in the bottom of shallow seas. The creatures that make it up, as they die, the skeletal parts remain and gradually get buried and crushed. And you can see the remains of a crinoid stem that is just folded up in the rock right here. That was a creature that stood upright on the sea floor and had a flower-like structure on top that filtered something out of the seawater. And the hard parts of that creature then, as it died, collected on the seafloor. And over time, that's what became these limestone layers, that and other creatures similar to it from that time period. Now, under enough heat and pressure, limestone becomes marble, and all fossil evidence then is eliminated. So this is a very old limestone, and that was what they had to quarry to mix with the iron in the furnace at Sloan.
So this is the Ruffner Mountain quarry from the top, looking down into the quarry. This is from Ruffner Mountain looking at Birmingham. And this is the Warrior River side of the mountain.